We are recording this class, that's good. Okay, so the challenge of the day is a couple of these problems that have things on a slope, multiple objects in them with friction and forces and accelerations and everything else. And I've looked at a couple of different people's homework, and it's been difficult to figure out where we're going wrong. One of the reasons for that is still, it's just difficult to work through other people's math homework. So we're going to do it again here and see if we can't get a correct answer. We'll do it all the way through and plug in numbers and everything and see if we can't get a correct answer. And we're going to look at some particular problems here. For example, did you guys do this problem? Number 25?
I got A, D, E.
Okay. And 24 was a problem that a lot of people struggled with, I think. Does anybody want to look at 24?
Yes.
Okay. I'm going to do this problem all the way through, and I'm going to check my answers right here in my open math so that we make sure that we've got a correct thing. And I'm going to do it in order because they always say that they want us to do it in order, even though I don't always do it in order. So we're going to do them in order. We're going to calculate everything in the order they want us to calculate it in so that we don't confuse anybody. So what is the force of friction on the box which is at rest on the incline shown below? I'm going to use...
That's cosine.
Hold on just a second. Let's first get to where I'm going to start this problem, which is going to be... Since I'm recording this, I want to make sure everybody can see it. All right. Let's see, why can't I do this here? Let's save this image. All right. Okay, here it is right here, right? Here's our picture. We're going to, I'd like to make that picture smaller. Can I make it smaller? Apparently not. Alright, well that's okay. We'll just go with it. Alright, so now we're going to... We've got an angle down here, theta, right? We're going to draw our free body diagram stuff. Here's our point for a free body diagram. We have our weight, which pulls down this direction. That's our weight. Right? And then we're going to show our axes. We're going to change our axes so that we have an axis that is perpendicular to our surface, and we're going to have an axis that is parallel to our surface. Right? We have one other thing in this thing that is friction, right? So which way is the friction going to point? Alright, this thing is going to try to slide down and to the right, so the friction is going to prevent that from doing that, and it's going to push upward to the right, upward to the left rather. So there's our frictional force right there. And the frictional force, I'm actually going to rewrite that really quick. I'm going to redraw that as a red force because it's in my parallel direction. So all my parallel forces are going to be in red. Does anybody have trouble reading the red? You good? Okay. All my parallel forces are going to be in red. All my perpendicular forces are going to be in green, so I can split it up into two problems. Remember now that when we build our components of our weight force, which is not, it's neither, the weight force is not perpendicular or parallel, it's somewhere in between, right? When we build the components for this, we need to have one component that is perpendicular, one that is parallel, and they need to meet up at this point, right? So we need one line that is perpendicular, one that is parallel, and they meet up at that point there. So the perpendicular one is going to go perpendicularly through that surface, and it's going to end right here so that I can make my parallel line this way, right? It's going to end right here so that I can make my parallel one that is parallel to this surface. Some of you drew this perpendicular one all the way down to here, and then you drew one this way. Well, this one's not parallel. That doesn't help us any. These two vectors will add to be the weight vector, but this other one's not parallel. So we need to not continue it too far. It needs to go all the way down to here, and that's going to be now called my weight parallel vector. Or sorry, my weight perpendicular vector. Then I can draw my parallel one from here to here, and that connects to my weight vector, and this is now my weight parallel vector. Okay, make sure that you draw it correctly so that you recognize where the angles are going to be, because this is the smaller angle of these two angles. This one is the smaller angle, so it's going to be theta up here, right? And then my weight parallel is the opposite side to that angle. So it's going to equal the weight of my thing, which is, I'm going to rewrite that as m times g, because the weight is mass times gravity. And then it's going to be, so that's the opposite side, so that's the sine of theta, right? Then my weight perpendicular is adjacent to that angle, so it's going to be m times g times cosine theta. So I've got those two fleshed out. I've got this one, my friction. Well, the friction force, this is friction, not parallel. My frictional force is a parallel force, and it's going to be equal to mu times the normal force. Well, what's the normal force? Where's the normal force in here? Well, the normal force is a perpendicular force that points perpendicular to the surfaces. So that's my normal force. And that's all my forces. Those are all the forces that I've got in this problem. So I'm going to work on now the parallel side. I'm just going to work on, no, I'll do the perpendicular side first. Perpendicular is going to be easier. So these are the perpendicular forces. What are they? The normal force, which is pointing in the positive perpendicular direction, and the weight force, which is in the negative perpendicular direction. So I add those together because that's the net force is in that perpendicular direction. Net perpendicular has to add together to equal the acceleration, right? Mass times acceleration. What's the mass times acceleration in that direction? What's the acceleration up and down? What's the acceleration here? Zero, because it's not going anywhere. This thing's not jumping off the surface, and it's not falling through the surface. So the acceleration is zero in the green direction, right? All it does is sit on that surface. It never jumps off of it, never falls through it. So that equals zero. And the net force, when I add all those forces together, what are all the forces? Well, I have the normal force, which is positive, right? The normal force, which is a positive normal. And then I have the perpendicular weight force, which is a negative force because it's going the opposite direction. That's minus m times g times the cosine of theta. Okay? Now before I move any further, let's go back to our problem, make sure we're going the right direction for this. One of the first things they ask us is the force of friction. To calculate the force of friction, we have to know the normal force. So I'm doing the right thing. I'm doing something that I need to do. So this equation, if I just take this equation right here, this part of the equation, this I can solve for the normal force. If I solve this equation for the normal force, I add mg cosine theta to both sides, and I get the normal force is equal to mg cosine theta, which you can get just from looking at the problem, really. But we just calculated it in a nice, clean fashion. So now I can calculate the normal force, and I can also calculate the friction force now, because the friction is equal to mu times n. So let's go ahead and calculate that.
Why is it drawn like that?
Right.
It's not going to go up a little bit. Why does the equation look like that?
What
I
equation?
understand that it's not accelerating, but then whenever you do mass times, then you're just figuring weight, right?
This is calculating part of the weight, yes. So what are you talking about?
Go up a little bit.
Go down here?
Yeah. Yeah. All right. So force net of your perpendicular equals mass times acceleration equals 0,
Yep.
which equals normal force.
So this right here is the net force. That's net force means you add the forces together. So I'm adding the forces together. This mass times acceleration equals 0. So these two things are the things that are equal to each other because the acceleration is 0 because it's not going anywhere, right? That's the thing that equals 0, and then the net force is this part. When you add those forces, they have to add to 0. They have to cancel each other out. And all this equation is telling me, all it's saying is that this force and this force have to cancel each other out because it's not going this way and it's not going this way. It's not moving in that direction. So it has to have an acceleration of 0. So that equation tells us something about the forces. They add together to cancel each other out, so they add together to equal 0. Then we can use that information to solve for the normal force. That tells us that the normal force is equal to m times g times cosine theta. Now this information can be used in our equation for the friction. The frictional equation says force equals the normal force, which is this right here. So when we replace n with m times g times cosine theta, and then you multiply by mu times mu. Now let's calculate. What's my mass? Well, go back to the problem. My mass is 46.6 kilograms. So I plug in 46.6 kilograms. And I would write it down. I wouldn't just plug this into your calculator. Because the more you do on your calculator, the less you can keep track of in your math.
Now why did you change to red?
Because the friction is in the red direction. 9.8 meters per second squared is our G. Cosine of, what's my theta? I don't know. We'll find out. 23.7 is my theta. Cosine of 23.7 degrees. Make sure that your calculator is in degree mode, if it isn't already. And then we multiply that whole thing times my coefficient of friction, which is, what is my coefficient of friction? Does it tell me my coefficient of friction?
No.
It doesn't. Okay. Okay. So we don't know what the coefficient of friction is, so we might not be quite done with this yet here, right? We're not done figuring this out. But that's a start anyway. So all we've discovered in this part is we've discovered that we don't quite know enough to calculate the friction using this information. That happens a lot in these kinds of problems where you go one way and you think you've got it, but then you realize you don't have quite enough information. When that happens to you, you go to the other side. We go to the parallel side and see if we can figure it out. So let's go to the parallel side and see if we can figure things out. On the parallel side, see if I can do this, here we go. On the parallel side, we have two forces, right? We have the force of the weight pulling it down to the right, that's a positive force, mg sine theta. And we have a friction pushing it up to the left, which is a negative one. And it says in the problem, what does it say that the acceleration is? It says it is at rest. So the acceleration is what? 0 again. So in the parallel direction, if we add up, if we have our force net in the parallel direction, net, there we go, equals mass times acceleration, the acceleration equals 0 again, right? So this has to equal 0. And then we add up the forces to equal 0. What are the forces? Well, we have our mg sine theta that's pushing it in the positive direction. Then we have for friction that is pushing it in the negative direction. Now for the friction, I'm just going to write it as friction because this is going to help me. If I write it as mu n, mu times the normal force, and then put a bunch of stuff in there, I'm going to realize that I don't have enough stuff to do the problem. Well, I will have enough stuff to do the problem, but I'll be solving for things I don't need. I just need to know the friction, so I'm just going to use this equation to solve for the friction. I'm going to add friction, add F to both sides, and I'm going to get F equals mg sine theta, and I know mg sine theta. I know those numbers, right? So I can solve for the friction right here and get part A done. I plug in my mass, which is turns out to be 46.6 kilograms. I know that, right? I know G is 9.8 meters per second squared. And I know the sine of 23.9 degrees. So now I can get part A. 23.7. I don't know. 23.7, you're right. Now I got a race.
And this is telling you the force of friction.
This is going to tell me my frictional force. 23.7 degrees. Okay, so that's part A right here. This is part A. We plug in the numbers. So let's plug in the numbers. To my calculator, my handy dandy
183.56.
183.56. And that should be newtons. So we go plug it in up here and we see if we're right. 183.56 newtons, right? Whoops. Okay. I'll try again. What was that, 24? 183.56, and let's see if we're right. Newtons return. Oh, it's not right. So let's try it again here really quick.
Oh, wait a second. Oh, that's fine. That's fine.
So that is correct. Let me try it with my calculator really quick.
That's what I came up with.
46, whoa.
Yeah, 183. But if you get your force of friction, don't you got to subtract that from your 100?
Nope. This actually should be the force of friction. Oh, so actually they probably wanted negative. Let's try that really quick. Since I didn't put in the sign. I'm going to try the sign negative and see if that gives me the correct answer. Does not. Okay, I'm going to do the calculation really quick on mine. Let's go back here. So M is 46.6, right? Times 9.8 times sine 23.7 into 83.56. Well, okay. Oh, wait a second. I have a different mass now. That's why. It just gave me a new mass and a new angle. So I have to put in a new mass and a new angle. Sorry about that. So I got to change the numbers here. So it's now 27.7. That's why I got it wrong. 27.7 times 9.8. 9.8 times the sine of, what's the new angle? 29.7.
How can friction be a negative though?
What's that?
Why would it be a negative? It doesn't come out mathematically.
Well, because of the direction, we know the direction. We were just calculating we were just calculating the magnitude. But also, let's see what it does for us. So actually, the answer should be 134 or negative 134. Let's put in a negative 134. And are they asking? They're not asking for the direction in this part because they asked the direction here. So it's 134.49 with these particular numbers since we changed it. So now let's see if we're right. And it looks like we're right. How about that? So the math is correct, even if I put in the wrong numbers. So this formula is correct right here. I just put in the numbers from the previous problem, and then it gave me a new problem. So this is not correct. But this is correct for part A. Okay? Now, what do they want to know next? They want to know what is the coefficient of friction, right? The minimum coefficient of friction required for this to happen. Well, the coefficient of static friction is from this part right here. It says that the friction has to equal mg cosine theta times mu. And we want to know what is mu. So we solve this equation for mu. So we go over here and solve this equation for mu. We're going to divide both sides by mg cosine theta.
So you divide your net friction, your regular equation is divided by friction on.
You can do that too. You can do it either way, it'll give you the same answer. So you could either do this right here, or you could do, so this mu equals your friction divided by mg cosine theta. Or you can take the number that you get for the friction, which was whatever it was, some number, and you could actually use this equation. No, actually you couldn't. You'd still have to divide, you'd have to divide this number by the normal force, which is this. You'd still have to do this. So this is the only way to really do it, because this is the normal force. So this is part B, so let's see if we get that. What was my number? 134.4 divided by m, which is 27.7. Divided by 27.7. And then I have to divide by the cosine, or divide by g too. Divide by, divide by 9.8 meters per second squared. Then I have to divide by the cosine of 29.7. And then I get an answer of 0.570 for my static coefficient of friction. Now, one of these problems, it tells you to give the units for coefficient of friction. Possibly, it might ask you to do that. What are the units for coefficient of friction? There are no units, so if it asks you for the units of coefficient of friction, just leave it blank. Okay? And then they want to know what the net force is. Well, the net force is all the forces on this block. According to our diagram and our calculations, these two forces cancel out to be zero, so the only net forces would be these two, but these two also cancel out to be zero. So what's your answer? Net force is, well, then they say if it was changed to 0.03. So now we have to change that. So this would be zero if we have this, if this is our coefficient of friction, but this is less than this one. So this is going to have less friction, which means it's going to slide now. Okay? So,
plug that into our
No, we can plug it into our equation for
friction.
the parallel forces. So the parallel forces equation was this one right here, but so this right here is our net force. So we can plug that number into this equation with the proper stuff in for the friction. So we're going to use this. We're going to use this right here to calculate the next part. And so let's go down here and plug it in. We're going to need a new page here. mg sine theta minus friction, right? So it's going to look like this. M times g times sine theta minus friction is our net force. But our friction is going to have to be written out as what friction is. Friction is the coefficient of friction, mu, times the normal force, right? And we already found out that the normal force is m times g times cosine theta. So we write it out like that. That's our normal force. We found that out from our perpendicular things. So this ends up being our net force right here. This is the force from gravity pulling it down. This is from gravity pulling it down the slope. That's what that force is. This right here is the force of friction. And it's pushing it up the slope. So they're in opposite directions. One's positive, one's negative. We want to calculate the net force, we plug in these things. So, what is our M? It was 20 something, 27.7. So we do 27.7. And then we multiply times G. And then we multiply times the sine of theta. It's supposed to have a theta on it. Sine of 29.7. 29.7. And then we subtract mu, which they give us as, they said the changes to 0.03, really tiny friction. So 0.03 is our mu. Then we multiply that times mass again, times 27.7, times g, 9.8, times the sine now, no, the cosine now, of theta, which was, what was theta again? 29.7. And then we do the math. And I got 127.4. Hopefully I got that right. Let's check it.
What area is that supposed to be in it?
What's that?
The air is supposed to be this way up the slope.
$127.4. And so which direction for the net force, right? So what would the direction for this net force be? Well, the friction is now less, right? So which way is this thing going to accelerate to?
Not the one down below. The one down below would be going down.
The one down below, which one? What are you talking about?
Right there.
This one?
Yeah.
Oh, the net force for this direction for the frictional force. So this one is trying to slide this way, so the friction will go upward to the left, right? This one, right? But this one is now, what's this one doing since it has almost no friction? What's this block going to do now? It's going to slide down, so the force is definitely going to be down to the right, correct? So let's check that really quick. Okay. So this is good. Let's see, how many attempts have they marked for me? 7 of 7. Cool. So every time you do it, if you do it individually, you get scored, you marked for an attempt. Huh? That's kind of stinky. I need to change that if I can. Okay, so now what is the acceleration of the object to the right? How are we going to calculate that? Well, we know the force, right? So how do you calculate acceleration if you know force?
Divided by mass.
Yep. You know that force net equals mass times acceleration, right? So you can just divide by the mass on both sides, and you will get the acceleration equals the force divided by mass. So our force, which is whatever it is, 127.4 divided by the mass, which is 27.7. So we divide by 27.7, and that equals 4.6. We put in our acceleration, 4.6. We put in meters per second, meters per second squared.
So it's just force net divided by mass.
Yep. Doesn't like the way I entered it.
Yeah, right.
Like that. Oh, I'm out of tries. But it is meters per second squared, whatever. I should message the instructor about this question.
Yeah, I need to message the instructor about mine because it looks like this is the second time this has happened. Go through everything and redo everything. See how everything went red?
Holy moly. Wait, what?
Why?
It redid your whole...
Yes, that's twice. I had it all done and actually understood it once. And then it did that. And I went through it again and my mind was just like,
Hold on, let me... You like chicken marsala, huh?
yeah,
I make a fantastic chicken marsala.
I don't understand.
Okay, let me check in my system to see if it's recorded your grade. Because if you had all greens, did you have all greens at some point?
Yes.
Usually that just records the first time it does it for me. Let me, when is this due anyway? Today? Tonight? Okay. Let me check to see the grades really quick and see if it's recording properly on my end. Because that's definitely either a system problem or an internet problem, one way or the other. Grade book, check 5. Scott, right? Holy crap. Well, I've got your answers in here marked correctly. I've got all your answers marked correctly, but it's still not giving you a score. Why is that?
That's twice. Not the first time.
Hold on, let me I think that I can enter it for you really quick. Let me see if I can submit this for you.
You know how stressful this is?
I can imagine.
Just came to the realization why I had so many issues on that one. I had to redo it twice before I got it right, and then forgot how I did it after I got it right. I forgot that the object wasn't moving, so therefore the force of friction was the same as the force of the parallel movement.
Okay, so it still has your answers in there correctly. Even though it's turned everything to this, it still has your answers in there. It just hasn't submitted them for some reason. So I will submit them for you. It even says it's submitted it. Why is it giving you 0 points? So I'll just submit them for you. That is goofy. Is anybody else having that problem where it sets everything to 0? That's really weird. I've never seen that happen before. Showing scored attempts. Is the program, is it subtracting points if you use multiple attempts?
Trig does, I don't think physics does.
Something's wrong with the program. Quiz. Homework. So let's see here. 2 attempts, no points taken off. 1 attempt. 3 attempts, no points. 1. Something. Okay. 0.7. Okay, so sometimes it's taking off points. Sometimes it's not taking off points. So there's something going on with the program. So I don't know what's going on with yours because you're the only one that's having this problem. So it's obviously not a system error. It could be something with the way your computer is sending information over the internet. And it's doing something goofy, but I have all of your answers correct in here the way they should be. And I will just go ahead and score it by hand. So,
If you give me to tomorrow, then I'll go ahead and redo it.
what's that?
If you give me to tomorrow, then I'll go ahead and redo it.
No, there's no point in you wasting your time. I can see that you got the answers right. I have them in here. It's just not grading them for some reason. I don't know why. So, I'm just going to go and give you the proper scores. It tells me everything you did, tells me the answers, how many attempts you made, tells me everything. So, I think on this homework assignment, it's not taking off points for multiple attempts from anybody. So I need to go in and fix something with it. I apologize for that mess up, but I don't know what's causing it, so we'll just have to move on and see if it happens again. We'll contact the guy that runs this thing and see if he has an idea of what that is all about. Otherwise, I'm just gonna score it. I'll just score you by hand on this. So. I'll do it problem by problem. Okay, so that was 24. Let's try to do some more here. Chapter 5. What's the next one we want to work on? So we're just moving down the row to 25 here. Okay, so this one is actually the same problem. The only thing that's different is that there's one added force. Okay. So,
Still, when I was trying to finish for a normal force, I was doing the same, mg times cosine theta.
Uh-huh.
And he didn't set minus.
For this one?
Yeah.
Okay. There's one other force that's added to this equation. added to this problem. So we have to figure that out. So let's, well, it's not really an added force, there's just an added thing that we have to think about. So let's go to our whiteboard here, and let's see, I used to be able to do this. Let's just go to a new page. Okay. Car on turn, open. All right, here's our car on the turn. So what forces do we have? Let's choose our coordinates. This will be our perpendicular coordinates. This is the part of our system. This will be our parallel coordinate system, right? And we have the weight of the car, which is down this way, right? Okay, so we have some parallel forces. What are our parallel forces?
Friction.
We have some friction that's going to push which way?
Up.
So the car is trying to slide down the slope, the friction is going to push up the slope, right? We also have a component of our weight that is going to be parallel, right? That one right there, the weight parallel. Any other? I don't think we have any others, right? Then we have a component of our weight that is perpendicular, that's this one. Weight perpendicular. Our angle in this problem is 16.2 down here, 16.2. And that's this angle right here, right? So that means our perpendicular weight, rather, is perpendicular weight is weight of this thing times the cosine of theta again, and then our parallel weight is weight sine theta. So we've set this up. This is exactly the same as we set it before. Our force is equal to mu times the normal force. We haven't put our normal force in there yet, so let's do that. Our normal force pushes upward on the car this way, right? So we've set it up exactly the same way as before. It's got all the same forces and everything else, just a car instead of a box. The difference in this problem is that one of the questions they ask is right here.
Long.
What's that?
Very long.
Yeah, we got a long problem here that says, turns out if the car wasn't moving, the normal force would be equal to the component force of gravity, and there would be some necessary friction to the tires of track, right? So we've set up this problem as if the car wasn't moving. That's what we've set up so far. But it is moving. It's turning around and around the track. And in order for it to stay going in that circle, there's an extra force involved. In order for this car to keep going around and around a circle, there's an extra force that's causing it to do this. What is the force that causes it to go in a circle? Well, let's see, they talk about that here. Where did it go? They call it a centripetal force, right? And what they say here is they say the getting turned by the 3D shape of the track, which makes the normal force larger than the weight of the car. The driver wants to go around at a perfect speed where it won't slide up and down, so it'll need a friction to maintain their height. What's the normal force of the car in this situation? Now, oh, so that's what, here they do talk about the centripetal acceleration. I didn't think they would. We don't have that in our wheelhouse yet.
It's like first part of chapter 6.
It is. But that's okay, let's do it anyway. So what causes we actually talked about this in the chapter on acceleration, or the chapter on forces. What causes something to move in a circle? What direction is the force that causes something to move in a circle? that direction of that force is towards the center of the circle. So we have another force that's this way. And we're going to call it the center force. Force center, right? We call it centripetal in physics. But we've just got an extra force in here that's causing this thing to turn around in a circle. And part of that force is a parallel direction force, and part of that force is an upward force, which really forces is a good word. It forces the car into the track. It actually creates so that it creates a larger normal force essentially on the car. So we get an extra normal force on the car, which makes the car seem like it is being pushed down into the track. But really what's happening is the track is pushing up on the car. Okay? So we have an extra force here, an extra normal force. Okay? So it means that the weight force seems like it weighs more. You could think of it as that. But really it's just an extra normal force. And so as you add in this extra force, that's going to require the car now. So now that the car is moving, this friction is no longer pushing this way, is it? If the car is going around the track tries to go higher on the track. Now the friction acts this direction instead of the other direction. Our friction is up here. So that changes this problem entirely. Now we have a friction that pushes down on the car from the top, and we have and so that friction force is actually equal to this force. Whoops. This friction force is part of the centripetal force. And the normal force is part of the centripetal force. So these two forces actually contribute to this. And now that I'm looking at this problem, I'm thinking we probably should save it for next chapter. Because it's just getting too much into the centripetal force. It's talking too much about this. We need to wait on that. We could still do it, I think, but I think the second part of the question actually throws this out of the window for this class. Because it says right here that it wants to do it at this certain speed. And can we do it? I don't think we can with the stuff we know right now. Yeah. Let's actually save that question for a later time. I'm going to take it out of the assessment right now. Sorry about that. I think that I should just remove it completely, but I haven't figured out how to do that yet. So if I withdraw it, all it does is cross it off. We'll give you all 3 points for that question.
Just going through these. I haven't been accurately depicting the split weight force parallel. Shoot me in the foot.
10, withdrawn. Okay, so do we want to look at 26? Okay, let's do 26. So we have two masses are not moving yet. We have the coefficient of the static friction. What's the maximum value at which the combined friction forces can fight this pull? So if it's fighting this pull, what do we know about the acceleration? since it's not moving yet, acceleration is 0, right? What's the first thing they want to know? The force of friction, net force, acceleration, tension in the rope. Okay. So, remember when we talked about defining systems. This is extremely important when you have multiple things in a system. For the first part of this problem, they want to know the friction acting on this, so we can define the whole. We can just define it as the whole system. Doesn't really matter all that much for the first part, I guess, because it's just the friction. But we'll just define it as the whole system here. So here's our system. Remember when we talked about defining a system, we said you're going to define what thing is your interest, and then all the forces will be the forces that are external to that. So I'm going to define this as my system right now. Oops, I crossed into the box. My system are the two boxes and the ropes, so I don't worry about the tension right now. Tension's not an issue right now. Only the things that are acting on the outside of the system are the issue. And the things that are acting on the outside of the system are a pull to the right of 318 newtons. So we got a pull out here, 318 newtons, right? We'll call that force P for pull, why not? And we have a friction. In which way is that friction acting? Opposite direction, because it's fighting the pull. And what do we know about the sum of our forces? Or the net force? Sum of the forces is the pull, positive force minus the friction, equals mass times acceleration. And what's the acceleration? 0. So it equals 0. This tells us that the pull equals what? The friction, right? Well, the pull, we know it's a number, 318 newtons, but the friction is always equal to mu times the normal force. Well, how do we calculate normal force? We look at the forces that are involved here, and we know that there's a weight force from this one. We'll call this, which numbers do they use here? M1 and M2. So this is 2, mass 2. Whoops. So this is weight 2, and this is weight 1. They both have a weight, and that there's a normal force on each of them. So we have to add them together. We have a normal force on 1. We have a normal force on 2. And since it's on a horizontal plane, what do we know about the normal forces? They're equal in magnitude to the weight, right? So if you add the weight and the normal force, it equals 0. When you solve that, you find that they're equal. So that this ends up being mu times the weights of these things. Mass 1 times gravity plus mass 2 times gravity. Okay? And that equals the pull from over here, right? Well, the pull is equal to 318 newtons. What are we trying to calculate? Let's go back and remember what we're trying to calculate. Oops. So the first thing we're trying to calculate is force of friction. So what have we got so far? Friction equals mu times
both
nu.
your forces down your rock or your weight.
Oh. Well, we already figured out what our friction is, didn't we? Just right there. We don't even need to do this. Our friction is equal to our pull, isn't it?
Yeah.
Because it's not moving. So what's our friction equal to?
318 newtons.
Yeah, that was beautiful. Good thing. Good thing I'm paying attention, huh?
Using that, we can calculate our total to make whatever.
Which direction is the friction?
Left side.
Left. Okay. What is the net force on the system then? We already calculated that too. What's the net force? What's the total force if it's not accelerating?
236.
So friction equals pull if it's not moving.
My friction didn't equal my pull.
Do you have, what is yours saying? Is that it's moving or not moving?
Alright.
Oh, wait a second, sorry. They're saying that it's not moving, but they're saying it's not moving yet, so it may be about to move. When they say it's not moving yet, that means they've just started to pull and there's been no time elapsed yet. So if it's going to move, it might move. If it's not going to move, then it won't move, but we don't know yet if it's going to move. So we have to decide if it's going to move. So we do actually have to do this calculation. So let's go ahead and do this calculation. We still have to do this calculation, but we know this calculation, we know this stuff. We don't have to figure out the mu or anything that's given to us. So we can just calculate the friction directly from this equation. Mu is given to us, what is it? I don't remember. 0.4, right? We put on our 0.4, mass 1 is 11.2, and then mass 2 is 25.1. So we have 11.2 times G, 9.8, plus 25.1 times 9.8. Add those together. We get like 350 times 0.4, so we get about 125, 175-ish, something like that. I don't know, I'll do the math. 11.2 times 9.8 plus 25.1 times 9.8 enter times 0.4 142. I was off by a little bit. 142. 142.3. Put that in right here for my force of friction, right? 142.3 newtons. Let's see if I'm right. $142.3. So that worked. Good. So now the net force on the system. Well, what's the net force if we now know the friction? We already calculated the net force to be P minus F right here, right? So this was not 0, we decided, because we don't know if it's moving or not. But we do know that the net force is P minus F, so it's 318 minus 142. So I do that, and I get 175.704. Plug that in, 175.7 newtons. In which direction is that going to be? Since the 318 is to the right, and it's the bigger one, the total is going to be to the right as well. So that's going to be to the right. And then what is the acceleration of the system? Since we have a total force of 175 newtons to the right, we can divide by the mass to get the total mass, to get the acceleration. The total mass is 11.2 plus 25, 11.1, right? So we divide by that. 11.2 plus 25.1, and then that gives us 4.84, I think, my number for the acceleration. Meters per
Write it
second.
out on the other page.
Yep, we can write it out, sorry. Okay, so this was our net force, right? That's how we calculated the net force. And then the net force is always equal to mass times acceleration. But we have two masses, so we have to add mass 1 plus mass 2 times acceleration. So the acceleration equals the net force divided by mass 1 plus mass 2. And that will give you the acceleration. In our case, our net force is 142 from here. No, it's 318 minus 142, which was 175, 170 something, whatever it was. Let's go back here and look at it. 175.7. So I take the 175.7 newtons. I'm going to divide by mass 1 plus mass 2, which is 11.2 Woo, 2 plus 25.1. 25.1.
And your force, that's your force of your pull subtract your friction.
That's correct. That's this one right here. And this gives me 4.84 meters per second squared. So that's the acceleration part right there. And I still haven't figured out how to enter meters per second squared. Do you just do meters per second like this? It does it? Okay. And that direction is going to be to the right as well, because that's the direction of the force, right? And then the magnitude of the tension in the rope. Now this is where most people get stuck. How do we calculate the magnitude of the tension in the rope? To do the tension, you have to define your system of interest differently. We have to look at a different system now. Here was our original system. Let's go to a new page, or let's just go down here a little bit. Put in a new picture. Put it in the same place up here. How do I go down? Whoa. Okay. So we have to define a new system of interest. Instead of defining our system of interest as the entire system, let's just do one system. We do know the force on this box to be forward. It still has a forward of 318 newtons this way, right? And it has a frictional force this way, just for this box. But it's affected by the tension back here. And from this previous problem, we also know that the net force, let's see, no, I can't. We know that the net force on this system, the total force pulling forward on this system, I don't want to do it that way. That's not going to work. So what we know about this, what we know just about this box is that there's a forward pulling force here, and that there's a friction pulling back here. But this friction that just pushes on this box is not the same as the friction we calculated before, because the friction we calculated before was the friction for two boxes. So we have to calculate this one separately. It's mu times just the mass of box 2 times g. That's the normal force on just this box. So we have to calculate a new friction force, and then we'll calculate a new net force. So that's our pull force, this is our friction force. But we have one more force pulling on it, and that's the tension force this way. Right?
But then you got to separate them, right? You're just using one box.
I'm using just one box, but this box still has the same acceleration as the two boxes. That's the thing that's the same, right? It still has the same acceleration, those two boxes. So if I add these forces together, I should still get the same acceleration. So I add the pull, which is forward, minus the friction, which is backwards, minus the tension, which is backwards, and I will still get the same mass. It'll be mass 2 times acceleration, because it has still the same acceleration. But I'm only talking about one box now. And the tension is going to take into account the friction on the back box and everything that has to do with the back box.
Isn't that tension basically the same magnitude as the net force of the first box?
No, it won't be exactly the same, but it'll be related to it. But this is the new equation we have to solve. So what is the pull? We know all these numbers except the tension. The pull is equal to, come on, there we go, 318 newtons, right? Wow. Good night. The friction is this thing right here, minus the mu times the mass of box 2 times gravity. We know those numbers. Then minus t, which we don't know, equals mass 2, which we know, times the acceleration we got from the first part of the problem. which is whatever it is, 4.84 meters per second squared, right? Times 4.84 meters per second squared. And we plug in our numbers. So I've got 318 is my first force, minus the mu, which was 0.04, 0.04, no, 0.4, right? My mass for mass 2 was 25.1. Gravity is 9.8. I should probably have solved this equation for t before I did this. Let's do that really quick. If I solve this equation for t, I'm going to add t to both sides, and I'm going to subtract this from both sides. So I'm going to get t equals, in the end, I'm going to get t equals,
Where's that 4.84 come from? That's your acceleration?
that's the acceleration from the first half. T equals 318 minus mu m2 g minus m2 times acceleration, which is the 4.84, right? So that's the equation I'm trying to solve now. And let's just erase this and do it again really quick. So this should give me the tension in the rope. 318 minus mu, which is 0.4, times mass 2, which is 25.1, times gravity, which is 9.8. 9.8. Goodness, it's hard to write with a mouse. Minus mass 2, which is 25.1. Times acceleration, which was 4.84 meters per second. Let's see if we get it right. 318 minus 0.4 times 25.1 times 9.8 minus 25.1 times 4.84 equals, I get 98.124. 98.1 units, newtons. All right, now let's submit and see how we did. Hey, we got it right.
You get back to the other.
Yep.
Still doing mass 1 is the left, mass 2 is the right.
Yeah, mass 1 is the left one, mass 2 is the right one.
So shouldn't the tension on the rope be equal for both sides?
Yeah, so the tension on the rope on this end is the same as the tension on the rope on this end.
But if you did it with the other box, it'd be the same.
If we did it for the other box, it would be the same. But instead of, let's see, on this, if we used this box, we would only have two forces. It would only be the tension pulling it forward and the friction pushing it backwards. So it wouldn't be the same equations. It wouldn't be the same way to solve it, but you would get the same number for the tension. And it turns out that if you do it that way, you discover something interesting, and that is that the tension in the rope is caused completely by the friction from the second box. In other words, if the second box had no mass and no friction, there would be no tension in the rope. So,
You don't want to accept my tension.
I'm sorry?
My tension is incorrect here, but everything else is fine.
So you use this equation here. Tension equals your pull force minus mu times m2 times g.
Right.
minus m2 times your acceleration. Oh, let's see your numbers here. So, what did you get for your?
No, I was 380.
Oh, yeah, you did.
Yeah.
Yeah. Dang it. Read that. Okay. Is everybody getting through that one okay at this point? What were we supposed to do today? Was today review day?
Yes.
So I guess we're doing review, right? Yours is not coming out right? So the tension is used at 234. There. 234. And then we're going to subtract off. Yours is 0.34. Times 1. What did you get for your acceleration? Did you ever check your acceleration, right? What do you get? I get 69. I think you have some possible misplaces. Entering it into the calculator, sometimes it goes one thing at a time right now. So put in this number, 69.6, and see if it I think that's correct. It's the one thing that I don't like about graphing calculators is they tend to be, well, they tend to think they're smarter than you are. So they start doing things for you in the calculator, so they start adding. So that's correct. But of course, it still tells you acting all the time.
Hey, but
So you bring your kids to the activity day Saturday? You know about it? Kids like love it. For parents, it's a lot of staying around and watching the That's simple, right?
supposed to be, it's slow to short walking back
So, also you just read it once and then just.
there. Yeah, but it's like when you're going like down to 10 is yeah, and
That is funny. Oh, I see what it's doing. It's saying that it's in the room. Okay, do it one that's do it one of these that needs to be put in. It's not here. Okay, so what it's saying, it thinks you're in review. You even know what to do for a while. nobody else is having problems with it shutting off your scores?
I think chapter number 2 or 3, whenever I did it, it just deleted everything. My scores, and it went like this. I could go back in and click one and get my answer.
Is anybody else using a Dell? Maybe that's the problem. Maybe the Dell computer doesn't like this thing.
I bought this computer from this college for $20. I put a solid state hard drive in it.
Yeah?
I upped the processor to the fastest I could get to that type socket. And this thing works flawless.
Nice.
And it's fast.
Except for your feet.
Yeah, except for your physics.
Yeah, shut up.
I heard it's possible for a girl to actually do it.
Well, I gotta do that.
We got them an Alienware award from the Headlights Gaming.
Yeah.
And something with the proprietary software they put in there for controlling the lights and everything screws up the ability to play YouTube. You
Oh.
cannot watch YouTube on a computer.
That's weird. See, I don't know enough about computer hardware to know if that could be the problem. But if it's only one person that's having that problem, it's got to be something with something that you're doing. I don't know what. And it could be an interplay between hardware and software, because whenever you're working with the internet, you know, anything can mess up that code that goes out of the internet. So, do you have all credit on all that? Looks like. Let me see if I can do something to save that here. Make sure that it's completed at this end.
Yeah, I'm mad at myself because I found this solution. It's a software conflict in the drivers. And I had it in my little tech notebook that I use for working on computers. And I lost the notebook. And then I had to reload the system. So now I've got to find the solution again.
Yeah, computers are trouble. And I really thought it would be a lot better since almost every computer company switched to the same kind of hardware format a few years ago. But
Can we do 27?
yeah, hold on just a second. Let me just take a look at your.
I was giving you full credit for one that I didn't even finish.
It did?
Yeah.
Now your computer's working for you, man. So you're not gonna come and complain about this problem anymore, right?
Yes. I'll be able to sell my computer to one of your physics students in the next class for like $1,000. $100 in it.
So what I can see on your homework assignment is that it gave you credit for. You have credit for the race car problem, but everybody got credit for that.
Yeah.
But it didn't give credit for
Look at
anything.
24.
24, you just finished.
No. Scroll down.
Oh, you don't have all the answers in, but it's still here. It doesn't. You don't have credit for it here. Oh wait, yeah, you do. It gave you 1 point, 1 full point. But way to go, man! You're awesome.
Hey, anybody that wants to do their homework on my computer, $20 an hour.
Listen, that's
You started to be treasurer.
Okay. So what did we want to do next?
27.
27. Is that just the next one? It is. Okay. They're not moving yet again. Okay, so they might move, right? Let's say this coefficient of static friction is 0.2. What's the maximum strength of friction for this situation? So when you have the maximum strength, you just use the coefficient at what it is, and you use the normal force at what it is, and calculate it, right? So the first thing they ask is, so how do we do that problem? How do we do the first part? All right. I'm actually in the wrong one anyway. 27. Okay. So for friction, for static friction, what's the equation? What's the equation for
Static.
That's almost.
Divide something by normal force.
it's friction static equals mu static times normal force, right? Very simple. For static friction, it has to be less than or equal to that, but if it's the maximum one, then it's just equal to that, right? For the maximum, we just put an equal sign in because that's the max. So what is the normal force in this situation? Well, we have mass down times gravity, which is the weight force, right? That's our weight. And then we have the normal force that goes up. Any other forces in that direction? Oops. Any other normal forces? Or any other forces? No. That's the only force. Those are the only two forces, so they have to cancel each other out because it's not going to go up or down, so the acceleration is 0. So the normal force is equal to the weight. So it's mu times S times mass 1 times gravity is the frictional static force. For my problem, that's 614 kilograms is the mass, and the mu is 0.27. So I have 0.27 times the mass, what was it, 614? 614. 0.27 times 614 kilograms times gravity, 9.8, and that's part A, meters per second. So we do that math, frictional force, we get 0.27 times 614 times 9.8 is 1,624 newtons. Excuse me. Of maximum frictional force. So this equals 1,624.
Oh, that's new.
1,624 newtons. And then what do they ask for next? Let's see. 1,624 newtons. Like that. Okay. What would be the maximum mass for M2 that this frictional force could hold up? So if we didn't know what the mass was here, right, and we just wanted to put one here that could be held up by this, what would it be?
Then you take it back and divide by gravity.
Well, let's figure out what we're trying to do here. What we're trying to say here is what kind of forces are on here? Well, the forces that are on here are the weight that's down, right? This is weight 2, which equals mass 2 times gravity. And we have the tension that's up. Well, the tension that's up here is caused by the friction here, right? So we have a frictional force this way and a tension this way, and the tension here is equal to the friction here. The friction causes the tension, right? So it's like the tension has to be equal to the mass times gravity, but the tension has to be equal to the friction. So the equation we're trying to solve is friction, which is this number right here, right? Has to equal mass 2 times gravity if we're going to hold that mass up. So that ends up being 1,624 newtons has to equal mass 2 times gravity. And then it's like you said, you just divide both sides by gravity, right? So when you do that, you get 1624 divided by 9.8 equals 165 for mass 2. So if mass 2 is less than 165, then it will hold it up, and that's the biggest mass it can hold up, 165.7. So we put that in. 165.7, and the units are newtons. Kilograms, sorry.
Yeah, kilograms.
Okay, so we got the number right anyway. Okay, so now we're going to use the value for M2, the actual one that they give us, that's here, which is much bigger than 165.7, right? And we're going to find the net force on the system. Okay? So we already know the force in tension that's on the system, or the force in friction. And now we're going to use the actual force in weight. So we go back to our whiteboard and we're going to look. We can use the whole system if we want, or we can just use this one block since we know what the tension is already. The tension is equal to this friction up here. So we've already figured out that the tension is equal to 1624 newtons. 1624 newtons. So we can just use this block to figure out the rest of it if we want. Because this system here is going to be has all the information we need. Well, this block has all the information we need. But our actual system is the whole system, so we have to include both masses whenever we use mass. Okay? So let's do a whole thing here. We're going to do the sum of the forces equals the mass total of the system times acceleration of the system. Well, the sum of the forces is equal to, we have a tension that's up, which is the 1624 newtons. We have a weight that is down, that's mass 2, right? So that's mass 2 times gravity down, and then that has to equal the total mass of the system, that's mass 1 plus mass 2, times the acceleration of the system, right? This is our net force on the system. So we just add these two things together to get our net force. So net force equals tension, which is 1624 newtons, minus mass 2, which is not there, it's over here, 869 kilograms. Ooh. 869 kilograms times G. Times 9.8.
Mass friction is static, right? The F NQ times gram.
Yes. So this is all before it starts to move. This is all right as the force is applied before it actually moves. So then I get 1624 minus 869 times 9.8. 1624 minus 869.8 times 9.8. So I've got negative 6,900 newtons. Negative 6,900 newtons. Okay, not correct. What did I do wrong there?
Put a negative on it.
Probably. There we go. 6,900 newtons. Because they wanted magnitude. I didn't read it correctly. They didn't want direction, they just wanted magnitude. Okay, now what will be the magnitude of the acceleration of the system? We go back here. No, we go back here. And we go back to this equation that has our acceleration in it. This one right here, right? This was our force net. That's this number right here, 6,900 newtons. So we would use 6,900 newtons for our force net on the left-hand side of the equation. And on the right-hand side of the equation, we have mass 1 plus mass 2 times acceleration, but we just want the acceleration. So we'll divide both sides by mass 1 plus mass 2. Mass 1 is 614, mass 2 is 869. So 614 plus 869 over here. We're dividing by the mass of the system, kilograms, and that equals acceleration. 6,900 divided by 614.
So your F net, all right, whenever you're doing the force equals mass times acceleration, your F net is your tension minus.
On this problem, yes. And that gives me a 4.65 for my acceleration. Let me just plug that in real quick and we'll come back to that. 4.65 meters per second squared. All right?
You said this is all being recorded for YouTube.
Can you go back to the other page and notice that?
So I went from here, my net force is just all the forces on the block in that situation. So we had tension up, weight 2 down, right? If we wanted to do the whole system, instead of tension up, it would have been friction and weight. Friction pulling the blocks this way, weight pulling the blocks this way, right? So it would work either way because the tension is equal to the friction. Since the tension is equal to the friction, then I just plugged in that number for the friction that I got for my force net, and I subtracted off the weight of the second block that's pulling it down. And I got the net force. Then I take the net force and divide it by the total weight, or total mass rather, to get the acceleration on the system. Newton's second law once again.
So that 6,900 number, that comes by M1 plus M2.
No, the 6,900 number came from this right here.
That's where you add the M2 gravity plus all of that.
I took the friction that we calculated up here, right here. I took the friction and I subtracted off the weight of the second block. So class is officially over.
So what is the T minus M2 gravity?
That's the net force. That's what I did right over here. That's this I just did over here. Then I used this equation again.
So that T minus mass 2 times gravity equals friction?
No, it equals net force. This right here is the friction. The tension and the friction are the same value.
Oh, you skip steps and you all.
I didn't skip steps, we're doing the previous steps from the previous part, we just didn't do them twice. So in the previous part, we learned that the friction is equal to the tension. And we learned that in the last problem too, which was the same kind of situation. In this problem, what we learned is that when we calculated the friction and then we looked at the problem, the friction and the tension are the same force, just in opposite directions. In other words, Newton's third law applies. The friction and the tension are the opposing forces in Newton's third law. So then we said the friction equals the tension. Then we used that number for the friction in this equation for the tension. So after we calculated the friction up here, we could calculate the tension. We could just plug it in for the tension because it's the same number.
The friction equals mass. I thought that was
Yeah.
numbers.
No, this is an equals. Because that's what the friction is equal to. Class is officially over, and I do have an appointment with a student at, I think, 11:50 or something. I have a student that may be coming to my office, so I've got to be in my office available for that student. But as soon as I'm done helping that student, I can come back in here and help with more homework if you would like me to. I'm going to assume that you would like me to.
Yes.
I'm going to go ahead and stop this recording, and I'll start a new one if we need to when we come back here.